Hi everybody. Today we're going to be looking at lesson number 41, power. Now the idea of power often gets misinterpreted by people simply because we hear terms like, the power company, that's where you get electricity from, right? But actually the power company isn't a power company. They are an electrical energy company that's supplying you with electrical energy. Power, as we will see, is actually a measurement of the rate at which you're using energy. So that means it really truly depends on, like in your home, what appliances you have on, what things you've turned on that are using electricity. That's power. That's the rate at which you're using the energy that is being supplied to you as electricity. Now, because power is a rate of change formula, it's the rate at which something is happening, it follows the same sort of pattern for a formula as the velocity and acceleration formulas do. Because you may recall that when we're talking about velocity and acceleration, they both are formulas that have something divided by t, because it's how much time does it take for something. So the same thing applies for power, because the formula is given two different ways: either work over time, it's the rate at which we are doing work, or because work is also delta E, a change in energy going through conversion, it's also a measurement of the power or the rate at which we are converting energy. So because work and energy are both measured in joules, that means that in both of these cases, we're talking about measuring joules per second. That's what the formula is actually doing. Now, instead of measuring power in joules per second, we instead decide to honor James Watt, a fellow who made some pretty good steam engines, and we name power, the unit at least, in his honor as watts. That's why when you look at something like a light bulb, it'll say 18 watts. Because what's that really telling you? It's telling you that that light bulb uses 18 joules of electrical energy for every second that it's turned on. Now we're going to see in the next section, that doesn't necessarily mean that you get 18 joules of light coming out, but it is telling you how much it's using. Anytime you see something on an electrical device that you're buying that says something about the watts that it runs at, that's what it's consuming. That's its input. So if I did have a 150 watt light bulb that I turned on for 2.5 hours, how much electrical energy did I use? Basically, how much work did it do for me? So what I would have to do is consider that what I've been given is the power, the rate at which energy is being used by this bulb, 150 joules every second that it's turned on, and that I turned it on for 2.5 hours. Now, unfortunately, most of that energy is going to be converted to heat, which is not the purpose of my light bulb, but that's something, again, to talk about when we get to efficiencies. But what I can still look at here is how much energy did it consume? How much work was it doing as a device? So I have to take my formula, multiply both sides by T. I'm solving for energy. And just so you know, one of the things that I prefer to do is I usually like to write the formula with energy on the top, delta E, instead of work, only because if I write a W here for work, power measured in watts, all these W's sometimes can kind of confuse people. You do you. It's cool either way. But just remember, energy or work done measured in joules as a unit, power measured in the unit watts. Okay, just be careful there. So I take my formula, start plugging in my numbers. 150 watts just goes straight in. I did have to convert the 2.5 hours into seconds, which isn't a big deal. There's 60 minutes in every hour. There's 60 seconds in every minute. So I basically go 60 times 60 times 2.5. I can set up a quick little ratio for that, and I get 9,000 seconds. Multiply that all out, and I get, with SIGDIGs, 1.4 times 10 to the 6 joules. That's 1.4 million joules of electrical energy used. Now, that's one light bulb turned on for 2.5 hours. That's got to make you think that when we're talking about electrical energy then, the amount of joules of energy that's actually used in a typical home even has to be enormous, like in a given month or something. And that's because a joule of energy actually isn't that much. So we do get these kind of shockingly big numbers here. So one of the things that we often kind of face is looking at situations where we're talking about power that's done by something, where there's a force being applied on the object just to make it move at a constant velocity. Think of something like a crane that's lifting up a load and it's just moving it upwards at a constant velocity, or a car driving down the street at a constant velocity. There's definitely forces being involved, work is being done. There's got to be some way of measuring the power then. So what we end up doing is something with this power formula that we don't do as often in a lot of the formulas. And what I did do here on purpose is I did write it as W, because what I wanted you to remember is a classic formula, W equals FD. I'm going to substitute that into there. So now I've got power equals force times displacement over time. Work is FD. Now, this is a common thing for us to do. We've taken one variable, a formula that we've got for that, and we've substituted in a couple of new variables. What we don't do nearly as often is look for something like this. When I look at this part of the formula, d over t, I've got two variables that I can replace with one variable, because I know d over t is v. That's velocity right there. So that means d over t can be replaced by velocity. So that means I've got a brand new formula. Power equals force times velocity. Now, if you're really on top of things here, this should cause you some concern for a moment, because usually when we talk about forces, Newton's second law, a force is being applied, it will cause acceleration. This is not a mistake. But it seems like it's a problem, because if I have acceleration happening, how can I have one constant uniform velocity? Well, here's the difference. What I didn't write when I did this or to this is I never wrote F net. That's not a net force. There can be all sorts of forces acting on the object, whatever it is in a question where I'm going to use this formula, but this force right here is tied in with the displacement. This is like an applied force. It's the force that's causing the displacement. And that does not necessarily mean that there aren't other forces like force of gravity or force of friction or whatever, but they're not responsible for the displacement. They're not part of the work being done. So that's why I can do this. This isn't saying F net. In fact, what we're going to see in a moment when we start solving some questions is that F net itself has to be zero in order to get constant uniform velocity. So in this particular version of the formula, I just need you to be really super careful that you're not going to treat this as F net. That's something that we've gotten used to doing in a lot of our work, where we're trying to find F net, and it's not the situation here. So I've got this example where I tell you that I'm using some sort of a motor hooked up with cables or whatever to try to lift bundles of shingles up onto a roof, because bundles of shingles are kind of clumsy and awkward to carry up on a ladder. The motor that I'm using is rated at 200 watts. Now, I know you don't necessarily think of motors that way. You think of like horsepower and stuff, but really in a metric country, that's the way we should be measuring it. And I'll show you some stuff with horsepower later. But what I'm doing is using that motor hooked up with, pulleys and cables and stuff like that to lift a bundle of shingles up onto the roof. I tell you that the bundle of shingles is 28 kilograms, and I'm lifting it up at that constant velocity, but I just don't know the velocity. I want to figure it out. So first thing I should do is figure out how much applied force is doing the work of causing the displacement of lifting that bundle of shingles up. So I know that there can't be any change in velocity, so F net has to be zero. That's the only way to say that we could be lifting things at constant velocity. That's basically Newton's first law, okay? So F net is equal to Fa plus Fg. I'm basically saying that the shingles have a force of gravity pulling down on them, and however this motor is doing it, it's applying a force to lift the shingles up. Sure, if it's a cable or something, we could be calling this force of tension in the cable. That's all cool. Okay, however it is that it's happening, though, there is an applied force coming from this motor that's lifting up those shingles. So if F net is 0, I look at the other side, Fa and Fg, adding them to get 0 basically means they're opposites of each other. One's positive, one's negative. They have to be the same magnitude, but they have to be opposite direction, but the same magnitude. So what I basically said is, let's like take one to the other side, where we would subtract it, and all I'm doing is I'm showing that Fa has to be equal to negative Fg. If you wrote Fg is equal to negative Fa, same thing. I wrote it this way, though, because I know what's about to happen in the formula that I'm about to play with. I can say that Fg is equal to mass times gravity, and then I put in that negative sign is just part of the formula. There it is, 28 kilograms, gravity, regular, negative 9.81, pointing down, gives me negative times negative, positive. Fa, the force that's pointing up, is positive, 274.68. I'm not doing any sig digs here because I'm not done the calculation yet. So I go on to the actual part where I'm going to figure out the velocity, P equals Fv, where remember, this has to be like the applied force that's causing the displacement, the applied force. So I manipulate my formula to velocity, P divided by F. I've got the power of the motor, 200 watts. I've got the force that's being applied in order to do this, 274.68. The velocity, after rounding off for a couple of sig digs, because of that, 0.73 meters per second. So it doesn't seem that fast, but if you're actually lifting up shingles, that's good enough for getting stuff up to the top of a roof pretty quickly. Now, this is where I try to bring in the horsepower thing a bit. We got to be careful because horsepower is not a metric unit. So I got to keep that in mind and probably do some sort of a conversion thing usually if I'm somehow dealing with it. So I'm telling you that I'm looking at a particular car that has an engine at 120 horsepower. So it's not a particularly powerful engine, but it's getting the job done. I am telling you that I've already gone through the conversion for you, and that's the same as 8.95 times 10 to the 4 watts. Now, that can sound weird, because I know that if somebody told you how many watts a car has, you're going to think it's an electric car, because that's the way we perceive wattage, okay? But what I'm telling you is that really horsepower is a measurement of power. It's just not a metric unit, and that if I convert it into the metric system, I get power in watts. And it does not have to be an electric motor for that, okay? So there's the number I'm going to be using. That's going to be its power. I tell you that the car is moving against friction because of air resistance, resistance with the ground, things like that. It's moving against all of that, and that it takes 4.00 times 10 to the 3 newtons to fight against that friction of the car moving along. But it's going at a constant velocity. Oh, so that's the kick again, that F net has to be 0, because if it's moving at a constant uniform velocity, F net has to be 0. Newton's first law. Fa plus Ff are what we're adding together to get the net force, and that means that once again, if I look at what's on this side, even though they are equal in magnitude, they have to be opposite in direction. I took one to the other side. So if I know that I'm fighting against this much friction, which I'm going to say is negative, just because that's the way we usually think of it, like backwards against the car, but the negative sign is already there, Fa is positive 4,000 newtons. Okay, so what am I going to do with that? P equals FV again. I have to take the formula, manipulate for velocity, power divided by force, and again, this is the force that is the cause of its displacement, the cause of its motion, which fits in with everything we were talking about for work. I've got the power divided by the force. I go ahead, smack those all into my calculator, and I get 22.4 meters per second, which is pretty good. We're getting up, I think that's getting up around 85, 90 kilometers per hour. Okay, that's just what it's doing then. A little bit of homework for you to look at. Hope everything is going well for you otherwise. Have a great day.